Okay, so I'm going to look at the Chapter 8 test review. You do have the whole week to complete this because there's a lot of questions on it. It's like 30 questions. But it covers everything, Chapter 8, Pythagorean theorem, geometric mean, and basic trigonometry. And then we also have these radical simplifying problems. So remember, with square root of 75, how would we want to go ahead and simplify that? We want to look for the largest perfect square that lives inside of 75. And we think about that, that would be 25. So I break that down into the square root of 25 times the square root of 3. So the square root of 25, since that's a perfect square, if that can come out, the square root of 3 is going to have to continue to live under there. Square root of 80 is going to be similar. I need to find the largest perfect square that goes into 80. So we could think about 8 times, or 4 times 20. But if we do that, we're going to realize that there's a bigger perfect square than 4 that goes into 80. There's another 4 that goes into 20. So our largest perfect square that goes into 80 evenly would be 16. So I'm going to break that down. And this is the part that most people will miss here. They forget when and where to get rid of that radical. So that's a 16 times 5. That gives me 80. Well, now because the 16 is a perfect square, we take the square root. Now the radical goes away, and we're just left with 4 square root of 5. Square root of 8, some of you might have this memorized by now, but we have the square root of 4 times the square root of 2, and again, 4 is that perfect square, so that just becomes 2 radical 2. Square root of 30, so this one fools people sometimes for some reason. Here's my perfect squares, I'm going to list them. And I'll stop here, but I could have stopped at 16. None of these divide evenly into 30. 4, 9, 16, none of them divide evenly into 30, so square root of 30 just stays that way. Square root of 32, sure, 4 would go into that, but the biggest perfect square that goes into 32 is 16. So this would be, take the square root of 16, that's 4, square root of 2. Square root of 12, we can break that into the square root of 4 times the square root of 3. It's 2 radical 3. 18 would divide evenly into 9 times 2. Square root of 9 is 3. He comes out. Square root of 2 continues to live under there. 108 divides evenly by 36. Okay? Good to probably have a calculator handy to do some of these. They won't simplify the radicals, but 36 times 3, I can just double check that. I can keep taking those perfect squares and dividing them into 108. Find the largest one that divides into 108. So the square root of 36 is just 6. Square root of 3. This should be an easy one for us to spot. 25 into 125. So 25 times 5 gives us 125. And that will just be 5 square root of 5. Another easy one to spot, in my opinion, are the 25s. We've got another one here. So this would just be 5 square root of 2. Okay, geometric mean, this is similar to what we were doing up above. We multiply two numbers, and then we take the square root of that. Okay? Well, here, conveniently, I get a perfect square when I multiply 2 and 8. I get 16. So this would just be 4. Okay? 9 and 36, I would recommend before multiplying them and getting a big, giant number, why not just put them both under radicals first? This might be easier for us to deal with. So I'm going to get the square root of 9, which is 3, and the square root of 36, which is 6. So I just get 3 times 6, which is 18. It's much easier to deal with. I might not recognize the 18 squared. So here I'm just going to lean on my calculator. So for the geometric mean between 4 and 7, for example, we would have the square root of 4 times 7, okay, which is the square root of 28. And then I'll just use my calculator to find the square root of 28. So the square root of 28 is 5.3. And I just use my calculator to do that. So here we would take 5 times 10. And we take the square root of that. So we want the square root of 50. It's almost a perfect square. Just missed it. It's a little bit bigger than 49. So if I take the square root of 50, that's 7.1. So again, we're going to round to one decimal place for these when we're rounding. Okay, so 28 times 14, pretty big number. but I'm just going to take the square root of that. 28 times 14, and I believe that that's 19.8. And last one, we multiply 7 times 36. We'll take the square root of that, and I think we find that to be 15.9. So now we move into the Pythagorean theorem situation, and anytime that I'm finding the hypotenuse, the biggest side, this is where I'm adding. So to find x here, I do the same thing every time. I'm going to take 9 squared plus 12 squared, and I'm just going to take the square root of that. Okay, and if you have the calculators that we used in class, if you have one of those or something like that, you can usually download a free version of that on the internet. You can just put that in one step. If not, you would do 9 squared plus 12 squared first, and then take the square root of that. Okay. Down here, I want to do both of these at the same time, so you can see this time I actually have the hypotenuse. I have the bigger side. So remember what happens here. I take 13 squared, and now I subtract 12 squared. See the difference? But every Pythagorean situation is going to be one of these two. You're either going to add or you're going to subtract. In both of these cases, I believe that you get 5 as your answer. I'm sorry, this one is 15, 225, right? We take the square root of 225 and get 15. Over here we do indeed get 5. So here, if I can, and I'll show you what this looks like on the calculator, if I can do 12 squared plus 32 squared and square root that all in one step, I will. If I can't, let me show you what that looks like in 2 steps. So what I did here was I did 12 squared plus 32 squared, and I got 1168. Then I take the square root of 1168 to one decimal place. That would be 34.2. Okay. Next one looks a little bit different, right? We have the hypotenuse, so what do we do now? 25 squared minus 12.5 squared. That's the only difference. And then I want to take the square root of that. So you can see 25 squared minus 12.5 squared. We take the square root of that, we should get 21.7. Okay, so here we still have a Pythagorean theorem situation, but we have to watch out. We're not going to use this 8 directly. What we have to recognize here is that that's a perpendicular bisector. If this is isosceles, that's 9 and 9, and we come perpendicular from that opposite vertice, it's a bisector. So that 8 is divided in 2. So I do have a Pythagorean setting. I have to subtract. 9 is the hypotenuse of that triangle. 9 squared, but minus 4 squared, not the 8 squared. Okay, so don't get fooled by that. We have 9 squared minus 4 squared, and then we'll take the square root of that. So hopefully we got 9 squared minus 4 squared, and we get 8.1 for that. So here I have 14 squared plus 31 squared, and if I'm still rounding to one decimal place, I think this is just 34.0. Or you could just say 34. You don't have to put the 0.0 there. Hopefully my solution key, I'll have both of those. So remember, the Pythagorean theorem says this. If I have a right triangle, this is A, B. The hypotenuse is always the largest side. And we know that C squared equals A squared plus B squared. But what happens to this triangle now if this angle becomes bigger than 90? If this angle becomes bigger than 90, think about what's going to happen here. This side C is going to get bigger. I don't have to change A or B at all. Leave A where he is, leave B where he is, so A squared plus B squared is the same. But if this angle gets bigger than 90 and we make it obtuse, C will get bigger. What happens in that situation then is that C squared is now bigger than A squared plus B squared. and that was because I turned the 90 into an obtuse angle. Likewise, if I go the other way, leave A and B alone, don't change their lengths, but just take this 90-degree angle and make it shorter, then C is going to have to get shorter. So when C is shorter, when I have C squared, that's actually less than A squared plus B squared. This is an acute triangle. So that's going to be our test. This one here is obtuse when we have this situation. And then when we have this situation, we have an acute triangle. Let's try and write it again. So we're putting this to the test each time. I have to compare 7 squared plus 24 squared to 25 squared. So what I find when I do 7 squared plus 24 squared, I get 625. And when I do 25 squared, I also get 625. So because they're equal, we have a right triangle. Okay? And let's not forget that the no triangle situation happens when the two smaller sides aren't at least as big as the third side. So we'll always make sure that we check for that first. I forgot to do that there, but 7 plus 24 easily is bigger than 25. 8 plus 14 is 22. So we're okay. We have a triangle. Is it right or is it acute? 8 squared plus 14 squared. How does that compare with 20 squared? This is 260. But 20 squared is 400. So what we see here is that that third side is bigger than the two smaller sides when they're squared. So if that's the case, then we have an obtuse triangle. Okay, you got that third side that's a good bit larger. Okay, so right away here, I notice I have 12.5 plus 13. Forget about squaring them just for a second here. What is this? This is 25.5. And the third side is 26. So if that's the case, this is a no triangle situation. The two smaller sides have to add up to be bigger than the third. Okay. And then the last one, we have some radicals invited to the party here. Now remember, square root of 16 is 4. So 4 has to be bigger than the square root of 7. Okay. And 3 square root of 2, if we want to figure out if that's bigger than 7, remember that that would be the square root of 18, right? So, and 4 is the square root of 16. So 3 square root of 2 is the largest side here. So let's square these out. I'll show you what happens if I have 3 square root of 2. Okay, so when I square the square root of 7, I just get 7. When I square 4, I get 16. So 7 plus 16 is 23. Let's compare that to 3 square root of 2 squared. So what happens here? 3 squared is 9. Root 2 squared is just 2. So this is 18. Or if you need to use your calculator, you can lean on your calculator for that. Either way, I find that 23, the two smaller sides, are bigger than the third side. This is where we have a acute triangle. So let's look at 20 squared plus 21 squared, and we'll compare that to 29 squared. I get 841 when I add these two together. And 29 squared is also 841. So when they're equal, we know we have the right triangle. Okay, so before I do too much work on this one, I look and see 32 plus 35. That is 67. And they're telling me the third side is 70. So since 67 is less than 70, this is no triangle. And our last part of chapter 8 was SOHCAHTOA, sine, cosine, and tangent, right? We have this acronym SOHC, which hopefully helps us to remember that the sine is the ratio of the side opposite that particular angle over the hypotenuse. Cosine is the side adjacent over the hypotenuse. And then tangent is just simply opposite over adjacent. We don't involve the hypotenuse with the tangent at all. So I have to observe what I have. I have this angle here at 36. The hypotenuse is not involved in the problem at all. I have the opposite side and I have the adjacent side. So I would like to use tangent for this. So I'm going to take the tangent of 36. And I want to make sure my calculator is in the degree mode. So I'm going to take the tangent of 36 and I'll write that up here to make sure you're getting the right number. Make sure you're in degree mode. You can use the calculator that's right on your computer for these. The tangent of 36, though, is going to be equal to the side that's opposite 36, which is x, over the side that's adjacent to it, which is 7. So to solve for x, I'm going to take 7 and multiply it by the tangent of 36. So making sure you're in degree mode, and if you have the TI-34, you have to hit second and the pi button, and you'll see the trig menu. But if you're in degree mode, which you're supposed to be, then the tangent of 36 should be 0.7265. So to solve for x, then, I would have to multiply by 7. Right? This is x divided by 7. So to solve for that, we would just take 7 times 0.7265. And just follow the directions round to the nearest tenth if necessary. So when I do that, I got 5.1. Okay, nearest tenth. So now let's take a look. We got 63. X is the hypotenuse, and 12 is opposite. 12 is opposite to 63, so this is going to be a sine situation. So I'm going to take the sine of 63, and what's that equal to? It's equal to the opposite over the hypotenuse, 12 over x. So I take the sine of 63, that's 0.891. That's equal to 12 over x. How do we solve for x? It's real simple. I say this to you guys in class all the time. 10, for example. Ten is equal to 20 divided by 2. So I can just switch those and write another truth statement that reads 2 is equal to 20 over 10. Both are truth statements. So that's all I'm going to do here. I need x, so he's going to come out. X is just going to be equal to 12 divided by 0.891. So 12 over 0.891, I got 13.5 for x there. Okay, we look at our angle 15. We have the hypotenuse and we have the opposite. This is a sine situation again. So we're going to start with the sine of 15 degrees. Equals the opposite side, x, over the hypotenuse, 12. So this one, we won't have to do the little switch here. We will be able to multiply to solve that. So I get 0.2588 equals x over 12. So to solve for x, we multiply. We would take 12 times 0.2588. And I get 3.1. Okay, so that's rounded to the nearest tenth. That's 1 decimal place. Okay, one more trig problem. We have 64 and we don't have a hypotenuse, so that means we have the opposite and the adjacent. So when I have the opposite and the adjacent, I'm using tangent, SOHCAHTOA. So we're going to write our true statement. We're going to say that the tangent of 64 equals the opposite from 64. The side that's opposite to 64 is the x, and the adjacent side is the 11, so he's going to go in the bottom. It's the opposite over the adjacent for tangent. So tangent of 64 is 2.05, and now we're just going to multiply to finish this off. To solve for x, we would just take 11, since we're dividing there, times 2.05. You don't have to do the swap there. And I get 22.55, which to the nearest tenth would be 22.6. Go to the nearest tenth. 22.6.